In 9.3, what we're going to do is we're going to look at how we can solve a special type of differential equation. And the differential equation is called separable. The reason why it's called separable is we can write the function y and its derivative as a product on one side of the equal sign, and then the variable on the other side. So if we can rewrite our equation this way, then the strategy is to integrate either side of the equal sign separately. So I'm going to go over what the solution would look like. So let's just say we do have a separable differential equation, meaning function y and its derivative on one side, function of the variable t on the other side. So that means I can take this equation and I can integrate both sides with respect to the variable t. So I'm going to integrate with respect to t on both sides. Okay, so remember what y prime is. Y prime of t is equal to the derivative of y with respect to the derivative of t. On the left-hand side, I can rewrite y prime as dy over dt. But notice I have this dt that will eventually cancel. And then I'll have the integral with respect to t dt on the other side. So the importance of this is that on one side of the equal sign we'll be integrating with respect to the function y, and on the other side of the equal sign we'll be integrating with respect to the variable t or x or whatever the variable is. So let's look at how we would apply this to example 1. So first of all, in example 1 it says determine if the equation is separable. So if it's separable, we should be able to bring the y and the derivative of y as a product on the left-hand side, which we can do if we just multiply both sides by 4y squared. Okay, and then I have e to the t on the right-hand side. So the derivative and the function y on the left is a product equal to anything with the variable t on the right. So yes, it is separable because I can separate them this way. So now what we're going to do is we're going to integrate both sides. But remember that this derivative is going to be replaced with dy. So this is the integral of 4y squared dy equal to the integral of e to the t dt. So 4y cubed over 3 is equal to e to the t. Normally we put a constant when we integrate. Now I don't want to put constants on both sides. The goal is to get y equal to something. So I'm just going to throw my constant on one side. And now my goal is to get y by itself. If I multiply both sides by 3/4, we get y cubed is equal to 3/4 times e to the t plus our constant c. And then all I have to do is cube root both sides to get y equal to the cube root of 3/4 e to the t, plus c. So y is equal to the cube root of 3/4 e to the t plus c. Now this is what we call our general solution. in order to solve for the constant c, we would have to have some initial conditions, which we don't have. So all we can do is find the general solution. If I could spell solution, sorry. Now let me just go over some alternate forms. Notice that I could distribute the 3/4 underneath the cube root and write 3/4 e to the t plus 3/4 times our constant c. Now remember, c is just some constant that we solve for if we have initial conditions. So if I have some constant number and I multiply it by 3/4, isn't that still a constant? So you can always play around with this and see if you can write it in a simpler form, such as a cube root of 3/4 e to the t plus a constant c. That's okay as well. But typically I'll just stop unless I see something that looks really nice. Typically I'll just stop here and not play with it anymore. Alright, let's go ahead and look at another example. So in example 2, we have to determine if the equation is separable. This time we do have initial conditions, so we can find a specific solution to this differential equation. So if it's separable, I should be able to get the y's on one side, which I can. If I divide by y squared, I get the derivative over y squared is equal to 1 over t squared. Oops, sorry. And this becomes the integral of y to the negative 2 dy integral of 1 over t squared plus 1 dt. And now on the left-hand side, I have negative 1 over y is equal to, so on the right-hand side, that's tangent inverse. So this is going to be tangent inverse of t plus our constant c. So there's something that's really nice with fractions, is that if I flip this fraction on the left-hand side, I can just flip everything on the right-hand side. So it's 1 over tangent inverse of t plus c. And then I can just go ahead and move the negative over. I've solved this for y. And this would be a general solution. To find the specific solution for our initial conditions, we have that y of 0 is equal to 2. Then I would just replace y with 2 and solve for c. 2 equal to negative 1 over tangent inverse of 0 plus c. So tangent inverse of 0 is 0. And I have 2 is equal to negative 1 over c. So solving for c, c is equal to negative 1/2. Putting all of this together, we have a solution of y. And if you want to add the variable t in, you can, to remind yourself that y is a function of t. So y of t is equal to negative 2 over 2 tangent inverse of t minus 1. And here I actually had tangent inverse of t minus 1/2, but I didn't like it written in that way. So in my head, I just did the algebra that would simplify this, because technically we're not supposed to have fraction within a fraction. That's not simplified. So in my head, I just multiplied everything by 2 to get the simplified version above. All right, let's go ahead and look at another example. In example 3, we're going to be looking at having multiple initial conditions. So if you have multiple initial conditions, you're going to get multiple solutions. Now we're going to determine if this equation is separable, and it looks like it is. This will be e to the y times the derivative with respect to the variable x is equal to cosine of x. Okay? So function of x on the right, all the functions with respect to y on the left. So I'm going to go ahead and integrate e to the y dy equal to the integral of cosine of x dx. We have e to the y is equal to sine of x plus our constant, c. So I need to get the y by itself. What I would do is I would natural log both sides, and that would give me y is equal to the natural log of sine of x plus our constant c. And this would be the general solution. But I do have initial conditions. I have one initial condition that y of 0 is equal to 1. So if I look at the initial condition that y of 0 is equal to 1, then my y is equal to, 1 is equal to natural log of sine of 0 plus our constant c. And sine of 0 is just 0. So we have 1 is equal to the natural log of c. And then exponentiating both sides, we have that c is equal to the constant e. So the specific solution for the initial value y of 0 is 1 would be y. And if you want to add in your variable x, you may, or just leave it as y. So y of x is equal to the natural log of sine of x plus the constant e. So let's look at the other initial condition and see if we can find a specific solution for those initial conditions. So this is y of pi over 2 is equal to 1/2. We have the equation 1/2 is equal to natural log of sine of pi over 2 plus the constant c. So we have 1/2 is equal to the natural log, sine of pi over 2 is just 1, of 1 plus c. So exponentiating both sides, we have e to the 1/2 is equal to 1 plus our constant c. And then c is going to be equal to e to the 1/2 minus 1. So the solution for this particular initial value would be y of x, if you want to put the variable in there, but you don't have to, equal to the natural log of sine of x plus e to the 1/2 minus 1. Just a heads up, sometimes my math lab forgets the absolute values. So sometimes you do need the absolute values and sometimes you don't. If we go back to this specific solution, sine of x goes between -1 and +1. So if I add e to it, which is about 2.72, what's in the absolute value is always going to be positive. So we don't have to worry about the absolute values here. So actually, we don't need absolute values. Okay, so it's sufficient to have parentheses. Again, that's because the argument's never going to be 0 or negative. So we don't have to worry about natural log being defined. I do need the absolute values for this one. And the reason why is because it's possible for this to be negative. And natural log can't be negative, it's not defined. So when in doubt, you can just leave them on. They don't hurt anything. So sometimes it's difficult for us to solve for y and get y by itself. And that would be the next example, in example 4. So this is what we call an implicit solution. Implicit just means we don't want to get y by itself. Okay, so sometimes it's difficult, or maybe it's impossible to get the y by itself. So example 4, we have the derivative of y times sine of y is equal to cosine squared sine x. Notice that this is already separated. Y is on one side, x is on the other. So I'm just going to integrate sine of y dy, okay? Because remember, we're replacing the derivative with dy equal to the sine of cosine squared sine, and this is dx. Now on the left-hand side, this is just going to be negative cosine of y equal to, for the right-hand side, I'm going to let u equal cosine of x. So the derivative is going to be negative sine of x. And this becomes negative integral of u squared du. Okay, but then the negative on either side of the equal sign can cancel. And we have the cosine of y is equal to u cubed over 3 plus c. And then I would just substitute back in my cosine. So cosine of y is equal to cosine cubed of x over 3 plus the constant c. Now, in order for me to solve for y, I'm going to need to take the cosine inverse on both sides, which I actually don't want to do, because then my domain is limited. Remember, cosine inverse only goes from 0 to pi, whereas in cosine, all real numbers. So because of that, I'm going to leave this in the implicit form. So I'm going to leave it as implicit. We do have some initial conditions. We have y of 0 is equal to pi over 3. So if y of 0 is pi over 3, That means where I see y, I'm going to plug in pi over 3. That would be equal to cosine cubed of 0 for x, right, over 3 plus the constant c. Cosine of pi over 3 is 1/2. So I have 1/2 is equal to cosine of 0 is 1, so this becomes 1/3 plus the constant c. And then solving for c, I have c is equal to 1/6. Now my implicit solution for those particular initial values will be cosine of y equal to cosine cubed of x over 3 plus 1/6. And we've solved that initial value problem. So I've used a graphing program to graph all the possible solution curves. And the solution curve that corresponds to that specific solution would be this curve here. Because when x is equal to 0, I'm at 1. Let's see, x is equal to 0, I'm at 1/3, x is equal to 0, 1/3 plus 1/6, yeah. So this would be my solution curve that corresponds to cosine of y equal to cosine cubed x over 3 plus 1/6. Something that comes up a lot in differential equations is the logistic equation. So logistic equations are population equations, right? But they have, and we looked at this before, they have this limiting factor, this carrying capacity. And the population can't go further than a certain point. So in example 5, we have 100 flies in a jar. P is going to be the number of flies in the jar t days later. The population can be modeled by this given differential equation. Okay, and then the initial population, P of 0 is 100, t is greater than or equal to 0. If we were to find the general solution, and this is going to be really long, okay, to this differential equation, well, the first thing I want to do is see if it's separable, and it actually is. Now I can leave the point 1 on the right hand side or just bring it over, but I think I'm going to leave it on the right hand side so that my computations are simpler on the left hand side. So if I divide both sides by p times 1 minus p over 600, what I get is 1 over p times 1 minus p over 600 times the derivative of p over t is equal to 0.1. So when I integrate both sides, it is separable. I get the integral of 1 over, and I think what I'm going to do instead of writing it that way, maybe I'm going to multiply top and bottom by 600 to make it look prettier. So actually I'm going to have 600 over p times 600 minus p. Again, that looks much nicer. dp is equal to the integral of 0.1 with respect to the variable t. Now, I don't know how to integrate 600 over p times 600 minus p, but if I use partial fraction decomposition, I can break it up into 1 over p, and I'm not showing the partial fraction decomposition. But if you'd like to verify it, you can go ahead and add those two fractions together. And then you'd get back to where we started from. So the integral of 0.1 is just 0.1t. And then we have this constant at the end here. This integral on the left-hand side is going to be the natural log of absolute value of p plus, oh, but what happens is this is actually going to turn into a minus because of the minus p, the 600 minus p. So it's going to be minus the natural log of the absolute value of 600 minus p. So that's going to be equal to 0.1 t plus our constant c. That's kind of long. Remember, my goal is to solve for p, and I've got p within both absolute values. So instead, what I'm going to do is I'm going to use properties of logs and bring this together as p over 600 minus p in the absolute values. So now I just have one natural log. And then I'm going to take the exponent e on both sides. So exponentiate both sides. When I do this, this becomes the absolute value of p over 600 minus p equal to e to the 0.1 t plus c. To get rid of the absolute values, I need to algebraically write plus and minus on the right-hand side. And I'm also going to break up e to the 0.1 t plus c as e to the c times e to 0.1 t, which I can do, right, by algebra rules. Now, e is about 2.72, and c is just a constant. If I add or subtract a constant, I still have a constant. So I'm going to replace this expression with just c. So on the right-hand side, this just becomes c e to the 0.1 t. Okay, and it's okay if we do this with general solutions. Depending on initial conditions, that would determine our c. All right. So I'm solving for p. Algebraically, I would just multiply both sides by 600 minus p. And this becomes p is equal to, and I'm going to distribute at the same time to write this as 600 c e to the 0.1 t minus p times c e to the 0.1 t. Bring all the p's to one side, so I would add p times c e to the 0.1 t to both sides. That would be equal to the 600 c e to the 0.1 t. And then on the left-hand side, I would factor out the common p. And then divide both sides by 1 plus c e to the 0.1 t. And I have p by itself. It doesn't look nice though. And the problem is that I've got c times e to the 0.1 t in both the numerator and the denominator. So although this is correct, and I did get the p by itself, and this is the general solution, I can clean it up a little bit. Okay. So again, this is the general solution, but let's go ahead and try to clean this up a little bit. If I divide both top and bottom by the constant c times e to the 0.1 t, what this will look like is p equal to 600 in the numerator over 1 divided by, oh, maybe I put my 1 too far away, divided by c e to the 0.1 t plus 1. And now I'm going to rewrite this, and when I do, I'm also going to take 1 over c and just replace it with the constant c. If 1 over c is a constant, then it's just the constant c. So p is equal to 600 over the constant c, e to the, I'm going to make it a negative exponent so I can bring this up. Alright, so that looks nicer. I'm going to let this be my general solution. Okay. The previous one is okay as well. I'm not sure how picky my math lab will be when you write the general solution. So this is just part A, finding the general solution. Now when we look at B, it says solve the initial value problem. Okay, so B, we have the initial value problem that P of 0 is equal to 100, which means 100 is equal to 600 over C. Remember, T is 0, so e to the negative 0.1 t is just e to the 0, which is 1. Solving for c, I get c plus 1 is equal to 600 divided by 100 is 6. C is equal to 5. And here, if you want to put p of t instead of just p to remind yourself it's a function of t, that's fine, but that's not necessary. So our specific solution would be 600 over 5 e to the negative 0.1 t plus 1. And that's it for this section. In the next section, we're going to look at another type of differential equation that we can solve for.